Great. How's everyone doing? Fantastic. Oh, that's better than I thought people would be doing. For me, I don't know. I'm lucky to have a yard during this shelter in place here in California, and I'm lucky to uh, be able to spend some time outside in my yard. And I've been messing around in the garden. And at first, I thought, I wasn't really into gardening, but I've been having a lot of fun actually. So, and learning so much about my own yard, all this stuff that I never knew about this place I live. It's great. I'm like lifting up rocks and seeing worms under them and sharing that with my daughter and feel like a little kid. All right. So, today we're going to talk about the Chandy-Lamport algorithm. We're going to wrap up our discussion of Chandy-Lamport. Uh, I have not found any slugs in my garden yet. I've found worms and other critters, like a caterpillar or two, but I don't have slugs, I don't think. Maybe like a snail. All right, so last time we went over the Chandy-Lamport snapshot algorithm, we worked out an example in detail. Today, I want to finish our discussion of it by talking a little about the bigger picture and the assumptions that the algorithm makes, and also a little bit more about what distributed snapshots are even good for. Um, so um, one so 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 one thing that we assumed, right, is that there's this notion of channels, right, and that channels have FIFO behavior. So what is a channel? Well, it's a connection from one process to another. And normally, when we draw Lamport diagrams, right, we just kind of there's not any special notation that we use to say that one process is connected to another. We just kind of assume that they are, right? So these processes are sending messages to one another, and there's nothing that we have to say that says, oh, by the way, process one can send a message to process two. We just assume that messages can go back and forth between all these processes however they want, and we don't have an explicit word for the thing that the messages travel through. But in the system model that we use for talking about the Chandy-Lamport algorithm, we had an explicit name for that thing, and that name was channel. And not only that, but channels impose this limitation on how messages travel through them. Channels impose FIFO ordering on messages that travel through them. So if this is process A and this is process B, and we have like message one and message two, then right now in the channel from A to B, that channel currently contains message one followed by message two in that order. So the channel is a sequence. It's ordered, and so if process A sends message one and then they send message two along that channel, they have to arrive in that order because that's what a channel is. We talked about that last time. Well, it turns out that this assumption that messages get delivered in FIFO order is a requirement for the Chandy-Lamport algorithm to work correctly. So if you have a setting where FIFO anomalies can happen, then you're not satisfying the prerequisites to run the algorithm. So one thing you might ask is, well, can you take a snapshot in those kinds of settings? If you have a setting where FIFO anomalies can happen, is there some other choice of snapshot algorithm to use? So there are snapshot algorithms that don't assume FIFO channels, but those algorithms might have other drawbacks. For example, one really nice thing about the Chandy-Lamport algorithm is that it can run at the same time as the application is running. And the application messages can keep on doing their thing and being sent even as the snapshot is taking place. So some other snapshot algorithms don't have that nice property. And so you can have this mixture, right? Like let's say that this is an application that's running right in the middle of this application running. A process could decide to start snapshotting itself and then send marker messages. And then this would be this is a nice property of the Chandy-Lamport algorithm, that these marker messages can be mixed in with the application messages. And my understanding from the literature on this topic is that if you want to allow non-FIFO messages, or if you want, excuse me, if you want to allow non-FIFO channels, then you have to pause application processes sometimes. So with Chandy-Lamport, you don't have to do that. So that's a trade-off, right? You can either impose this FIFO requirement and then not have to pause anything, or you could not impose the FIFO requirement and then maybe have to pause things in order to take a snapshot. So that's one of the assumptions that we make. Channels are FIFO. What other assumptions do we have to make in order to run the Chandy-Lamport algorithm and expect it to work? We started to talk about this a little bit last time. Yeah, okay, so reliable delivery. Yeah. Reliable delivery of messages. So messages aren't lost. And then we also, kind of along with that, we assume other things. We assume that no Byzantine behavior happens, right? We assume that messages aren't corrupted. And we also assume that messages aren't duplicated. So no message loss, corruption, or duplication. Anything else we have to assume? We haven't really started to talk about fault models yet, and so I'm thinking ahead to when we start to talk about fault models. So one of the kinds of faults that we're going to talk about is processes themselves crashing. So that's another assumption that's being made here. So some distributed algorithms are robust to some number of the processes in them crashing while they run. But this is not one such algorithm. So you might wonder if this is kind of a crappy distributed algorithm, if it can't stand up to these things like process failure or message loss. But it was the first distributed snapshot algorithm, and it was groundbreaking at the time. And it does hold up even if messages are arbitrarily delayed, which is a pretty big deal. Okay, so these are assumptions that the algorithm makes, or if you like, they're limitations of the algorithm. But just so that things aren't all doom and gloom, let's talk about some good things about this algorithm. So we talked a little bit about termination last time, briefly. So just to talk about that again, just very quickly, this algorithm is guaranteed to terminate. And we're not going to put forth a formal argument or a formal proof of that, but just to informally discuss why we know it terminates. Well, okay, so what does it have to do, right? It has to record the state of every process, and it has to record the state of every channel. And every process is responsible for recording its own state and the state of its incoming channels. So if you can argue that that terminates for every process, if every process can have its own piece of the algorithm terminate, then it follows that the whole thing terminates. So do we know that that terminates? Yeah, it does. So recording its own state is pretty straightforward. And then recording the state of its incoming channels, given these assumptions, right, that messages aren't lost, we know you're going to get a first marker message, you record your own state, and then when you record the state of your incoming channels, you know you're going to receive a marker of you're going to receive a marker message on all your incoming channels sooner or later. So basically, once everybody receives a marker on every one of their incoming channels, then you're on the way to being done, right? And we know that everyone receives a marker on all its incoming channels because that's how the algorithm works, and we're assuming reliable delivery. So that's the informal argument for this happening. So in their paper, Chandy and Lamport say, if the communication graph is strongly connected, and at least one process starts, right? At least one process begins by recording its state, then all processes will record their states in finite time, assuming reliable delivery. So when they say the communication graph is strongly connected, they mean that every process is reachable from every other process via channels. And we have been assuming that that's true. We've already assumed that there's a channel between every two processes. So in fact, in our case, the communication graph is not only strongly connected, it's actually a complete graph. So to draw a picture of our processes as if they were a graph, we've been assuming that every process has a channel with every other process to and from. So we've been assuming that the graph of processes, where processes are nodes and channels are edges in the graph, we've been assuming that it looks like this. So Chandy and Lamport only say that the communication graph has to be strongly connected. So they say you could have something like this. Let's say. And this would be, you could simulate this one up here. So this one is a complete graph. This one is not complete, but strongly connected. So if you had something like the bottom one that's strongly connected, you could simulate this one up here. Like if you needed to send a message from P3 to P2, you would have to go around through P1. So this up here is actually the only one that they require for the algorithm. But when we talk about the algorithm, we kind of just assume that we have, or excuse me, I mean, this is what they assume. This is what the Chandy-Lamport algorithm assumes. But when we talk about it, we make the simplifying assumption that we have a channel between every two processes. Okay, so we're not actually going to do a proof that the algorithm terminates, but if you're unconvinced, I encourage you to go think about it on your own. There's an interesting thing that I want to talk about next with this algorithm. So what Chandy and Lamport say is they say that at least one process has to start by recording its state, right? So I think it's very interesting that they said at least one, right? They didn't say it had to be one. They said it had to be at least one, has to begin by recording its state. And that's the initiator process that we talked about last time. So of course there has to be one, right? Obviously, in order for the algorithm to run, it has to start somewhere. But it's very interesting that they say that it doesn't have to be exactly one, it has to be at least one. So in the examples that we worked through last time, we picked one particular initiator process to be the one to record its state first and send out marker messages. But what if more than one did that? What if multiple processes said at the same time, okay, I'm going to start taking a snapshot now? Would that be okay? And so the answer is yes. So just as an example, if we had P1 and P2, processes 1 and 2, and they both decided to initiate a snapshot at the same time. So let's say that process 1 had some events. Process 2 has an event. And let's say they both decide to initiate the Chandy-Lamport snapshot algorithm at the same time. So process 1 snapshots its state, and it sends out a marker message. Process 2 snapshots its state, and it sends out a marker message. Okay, so they've both sent markers to each other. So recall that when you're, let's make this a little bit more interesting. Let's add a message here as well. We'll call this D. So recall that when you're an initiator and you record your state, you have to send out markers before you do anything else. So in particular, P2 here has to send out this marker message right here after it records its state. So when it recorded its state, event D hadn't happened yet, and then it had to send out the marker message before event D could happen. Okay, so good so far. When they send out their markers, they start recording their incoming messages. Okay, so now process 2 can, after it's sent out its marker here, it starts recording. So this is the point right here where it begins recording. So now it records this incoming message from B to D on channel C12. So message from B to D becomes part of its this channel history. Then they each get each other's markers, right? And then they can each stop recording. So C21's channel state ended up empty because it didn't receive any messages while it was recording. And now we have a complete snapshot. Is it a correct snapshot? Yes, it actually is. It corresponds to a what we call a consistent cut, which we'll talk about in a minute. So is there any way that we could have ended up with a bad snapshot here? Like if P1 and P2 had both initiated the snapshot, could you have ended up with something wrong? So an example of something wrong might be like if this looked like this and then C and D. So this would be a bad snapshot here. So what's wrong with this? What's wrong with it is that D is in the snapshot, but B, which happened before D, is not. So this is a bad snapshot. Could you end up with this if both process 1 and process 2 initiated at the same time? No, you couldn't, because after P1 takes its snapshot here, it has to send its marker message to P2 before doing anything else. And that message can't do this, right? It can't cross over like this because of FIFO delivery. So in this case, process 2 would have to get the marker message somewhere up here, somewhere between C and D. And what do you have to do when you get your first marker message? You have to record your state. So the picture would have to look like this over here. It would have to look like this instead. So it would have to correspond to what we call a consistent cut. So it's actually fine to have multiple processes initiate. And this is huge. Why? Why is it such a big deal that multiple processes can initiate this snapshot algorithm and it'll still work? So here's why I think it's a big deal. What if that wasn't true? What if it wasn't the case that multiple processes could initiate at the same time like this and it would still work? Well, then suppose that somebody wanted to take a snapshot, right? They would have to go around to everybody and say, hey, I'm going to take a snapshot now. Is that okay? And then what if, while it's waiting to hear back from everybody to tell them that it's okay, what if it gets a message from one of them saying, hey, I'm going to take a snapshot? And then things get really chaotic, right? So what it boils down to is, if it's not okay for multiple processes to initiate a snapshot at the same time, then the processes will need some kind of way of deciding who will initiate. And it turns out that that, in and of itself, is a case of a challenging class of problems called agreement problems in distributed systems, which we're going to talk about more later in the course. But because this algorithm works just fine with multiple initiators, it turns out, we don't have to worry about any of that. So processes don't have to agree on who will initiate. If they want to initiate, they just go ahead and do it. So there's a question in chat, which is, do the marker messages have to include an identifier for the snapshot initiator? So I don't think so, because I mean, who cares, right? Like if you get, if the algorithm here is running, right, and this process initiated and so did this one, they both sent out their marker messages. I don't think process one cares that this marker message originated from a different initiator. I think the algorithm still works fine without that. I don't recall there being anything in the Chandy-Lamport paper about there needing to be a, an initiator identifier on these marker messages. I think the marker messages can just be undifferentiated. So, yeah, go ahead. Uh-huh. Yeah. Um, uh, okay, so, right, okay, so right here, the question is, does process one know, so if process one doesn't know whether this is a marker that's a response to its marker, or whether it's, okay, let's say on process two. So process two doesn't know whether this message coming in here is a response to its marker message or not. Um, okay, but okay, so let's say it does close this channel right here. Um, I don't think this is necessarily a problem, right? So it's closing the channel from S1. Um, so I don't, another message. Okay, let's say there's another message here. Mm-hmm. So maybe you would. So I would agree that maybe you would want it to be there, but I don't think you would end up with an inconsistent snapshot if it wasn't there. So I think that if you do initiate if you do have multiple initiators, I think uh, your snapshot be might be smaller than the ideal, right? In the sense that it's going to capture less, right? Because marker messages arrived arguably faster than they would have otherwise. Uh, but um, but I don't think that I don't I but it wouldn't. So even though it might be a smaller snapshot in the sense that it captured a kind of a smaller prefix of event history, I don't think it would be a wrong snapshot. Well, yeah, but when are you ever going to have a complete snapshot, right? Like there's always going to be like these snapshot, there's no guarantee with this snapshot algorithm that it's going to be like the most up-to-date snapshot, because what does that even mean? Unless you paused everything and then decided to, if you paused everything, then you could snapshot everything that you had, but that would require you to pause. So there's another question in chat, which is, wouldn't you need an identifier to figure out which snapshots to group together? So no, I don't think so. I mean, so when a message arrives, you know who it came from, right? Because you know which channel it came in on. So you know, for example, when P1 receives a marker message from P2, it knows to close its incoming channel from P2. And then these snapshots, the snapshots of the state that's taken on each process, well, you're going to have exactly one of those for every process, no matter what you do. So it's not as though the snapshot on the process gets taken a second time when you receive the other initiator. It's just once it's already there, it's there. So there's no need to then snapshot the state again when you receive another message, because it's like this process, as far as it's concerned, when it gets this other message here, it doesn't know that process 2 was also an initiator, right? It just knows that it's receiving a marker message, and then it just does the standard thing that it does when it receives a marker message. In this case, it's a marker message, and because it sent this one, it's the case where you receive a marker message and you've already seen one. So you all are asking really good questions about this, actually. And I admit I haven't thought through all the details. But in general, this you might have to trust me when I say this algorithm has the property that you can have multiple initiators. So I think this is really, really very deep, right? The fact that that this algorithm could run in this way that doesn't require the processes to have to agree on who will be in charge. So if somebody wants to initiate, they just go ahead and do it. And if more than one does, then it's not a problem. So algorithms that have this property are called decentralized algorithms. So the simplest definition, there's different ways to define decentralized, right? But the simplest way to define it that I know is a decentralized algorithm is one that can have multiple initiators. And so by contrast, a centralized algorithm has exactly one initiator. So the Chandy-Lamport algorithm is a decentralized algorithm. Not every distributed algorithm is, but this one is. And we'll talk about other decentralized algorithms later on in the course too. Okay, so another thing I want to do before we move on from discussing snapshots is just say a little bit more about why we want to have snapshots in the first place. So we started to talk about this a little bit last time, but let's talk about it a little bit more. So what's the purpose of taking a snapshot? What are snapshots good for? So here's some ideas. Checkpointing. We actually talked about this a little bit at the beginning of the class on when we talked about HPC, high performance computing systems. So some systems take periodic snapshots of their state so that if they fail and have to restart, then they have a reasonable place to start from instead of having to start from scratch. So a snapshot algorithm could be used for that. Here's another thing. Deadlock detection. So the state of being deadlocked is a property where once it's true at one time, it's going to be true from that point onward as long as the system is running. So a deadlock would be a situation where one process is waiting for another, and then that process is waiting for the first one, or maybe you have a group of processes that are all waiting on one another. So you can check for deadlocks by periodically taking a snapshot and then seeing if there's a deadlock in the snapshot. So if a snapshot has a deadlock and the system is still running, then the current state of the system will also have a deadlock. And then more broadly, actually, so generalizing that, detection of any stable property. So a stable property is any property of a system that once it becomes true, remains true from then on. So deadlocks are actually, the property, the system is deadlocked, is an example of a stable property. So snapshots can be used not only for deadlock detection, but they can be used for detecting whether any stable property of a system is true, in the same way that they can be used for deadlock detection. So another example of a stable property is the system has finished doing useful work. Um, in other words, termination. So that's another stable property that we could detect using snapshots. We can take a snapshot, and if there's no useful work continuing in the snapshot, now that's not necessarily something like that's something that might require a human, right, to know whether it's useful work or not. But that's another stable property that we can detect using snapshots. So there's a question in chat, which is that since the Chandy-Lamport algorithm doesn't work if the system crashes, does that mean we can't use it for deadlock detection? So when you say a system crashes, yeah, so I'm guessing you mean a process crashes. So let's say you're trying to run the Chandy-Lamport algorithm and a process crashes. Well, what you have to do is start over. So in other words, the Chandy-Lamport algorithm isn't robust to a process crashing. So you can use it. So I guess, so I think maybe, perhaps I should have used the word live lock here, but maybe you're conflating deadlock with crashing. So if a process crashes while you're trying to take a snapshot, then either the Chandy-Lamport algorithm won't terminate, right? Because it'll be waiting for a marker message from that crashed process that will never arrive. Or I guess it's also possible that the snapshot will be wrong in some way, although I haven't thought through the details of that. But uh, but I don't. I think those are distinct things. I don't think that that the requirement that that processes don't crash while the snapshot algorithm is running, I don't think that interferes with our ability to use snapshots for deadlock detection. All right. So that's about it that I have to say about Chandy-Lamport. I'm going to pause now and do a quiz question. So I'm curious about the ratio of people who are watching on Twitch right now versus watching on Zoom for people who are enrolled in the class. Because it seems like there's, yeah, okay, so there's 70 people in the Zoom meeting right now, which is the majority of the class. But I wonder how many people are actually watching on Twitch. I've only talked to a couple of students who say that they watch on Twitch, but maybe there's actually a lot and I just don't realize it. People are saying that the Twitch video is so much better. Isn't that amazing? One of my incoming grad students actually works at Twitch. And he introduced me to somebody who I asked to give a guest lecture in this class about how Twitch works. And I really wanted to make that happen, and that person was enthusiastic about it too. But it turns out they won't be able to do it until fall. So maybe I'll get somebody from Twitch to come guest lecture in my graduate distributed systems course in the fall, which would be awesome. Unfortunately, it can't happen this spring. So when Twitch reports the number of viewers, does that include just people who are watching it in the browser and not logged into Twitch? I guess it does, right? All right. Cool. So that's like, I guess, added together the Zoom plus Twitch, that's like the whole enrollment for the class. So assuming that like at least some percentage of people who are enrolled aren't watching, um, hopefully other people who are watching on Twitch are just random people from out in the world. So hi, random people. All right. We're going to wait another few seconds, and then we're going to move on to our next topic. All right, let's move on. So when we started to talk about Chandy-Lamport, I claimed that it had something to do with causality. And this set of events that are in a snapshot taken by the Chandy-Lamport algorithm, they're always going to make sense with respect to causality. So here's what that means to be more precise. So let's say you have 3 processes and some events and messages. The actual set of events and messages here doesn't really matter. It's just an example. So we're going to define a new piece of terminology here. So a cut is a time frontier going across a Lamport diagram. Dividing it into past and future. So here's an example of a cut. It's just a dotted line that goes through here. So it cuts across every process at some point. So this would be past and this would be future. So we say that an event is in the cut if it's on the past side of the cut. So for diagrams done the way that I draw them, that means above the line, because I always draw with time going downward. So an event is in the cut if it's on the past side. That's the definition of that term, in the cut. So what do you think it means for a cut to be consistent? So we're going to define consistency this way. We'll say a cut is consistent when for all events, say E, that are in the cut, if F happened before E, then F is also in the cut. So if we say if F happens before E for all F, then F is also in the cut. So in a consistent cut, you can't have this. So if I have something like this, I couldn't have something like this as my cut. Right, because this event here is in the cut, right, because it's on the past side. So this event, if we give these processes names, then the event on process 2 is in the cut, right, because it's on the past side of the line. But this event over here is not in the cut because it's on the future side of the line. But it happened before this event, according to the happens before relation. So this would be an inconsistent cut. But something like this would be okay. So here, the event on process 2 happened after the event on process 1, and the cut, then the message goes across the cut. So that's actually allowed to have a message going across the cut that way. So here's a fact about the Chandy-Lamport algorithm. The Chandy-Lamport algorithm determines a consistent cut. So in other words, if you take the set of events in a Chandy-Lamport snapshot, so the snapshot, right, consists of snapshots of states of the processes and then snapshots of the channels. So if you take the set of the events that are in the snapshots of the states of the processes and you make a cut and that set of events is in the cut, then that cut is going to be consistent. That's what we mean when we say the Chandy-Lamport algorithm determines a consistent cut. So you can look at that in the example that we went through last time for the Chandy-Lamport algorithm. So this picture. So we can look at this and we can see that there's a consistent cut here. So you could draw your cut as a dotted line across this picture. And we can see that it's a consistent cut. So in some cases, we have messages that are going across the cut, right? But we don't have any case where there's a message that happened on the future side that went over to the past side. So we see that it's a consistent cut. And plus, the Chandy-Lamport algorithm has this additional property such that if there is a message across the cut from past to future, like here with this H to D here, then it's going to be captured in a channel recording. So the snapshot will, in some sense, it'll know about those receive events as well. But Chandy-Lamport will always give us a global snapshot of processes that corresponds to a consistent cut. So you might hear somebody say that the Chandy-Lamport algorithm is causally correct, or that the snapshots that it produces are causally correct. Oh, a question in chat was, how do you determine where to place the cut? Well, in the line that I just drew here, I just did a cut is just a line that crosses over every process line at a particular point. So I had it cross over every process line right after the events that were in the snapshot of the state of each process. So I had it here between B and C because A and B were in the snapshot of the state of process 1 and C wasn't. And then here, this was actually the last event on this process, so I did it under there. And then here I was in the snapshot, but J wasn't, so I did it in between I and J. So that's the cut that's determined by the algorithm. And then that cut, it's a property of the Chandy-Lamport algorithm that if you draw that cut, the one that's determined by the snapshot that was taken, then it will be a consistent cut. Okay. Questions about that? Okay. So we have maybe 15 minutes left. I want to start to get ready to move on to a new topic. But in the time that we have left, we won't have time to go into a whole lot of detail. So let's just recap some of the things that we've been talking about the last few days, and then we'll be in a good place to move on to a new topic next week. So let's quickly recap the delivery guarantees that we've talked about so far and the protocols that enforce those guarantees. So the first one we talked about is FIFO. And what does the FIFO guarantee say? It says if a process sends, say, message M2, after M1, then any process delivering both delivers M1 first. And the Lamport diagram that illustrates a violation of this guarantee would look like this. So that's a FIFO anomaly. And what do we do to implement a FIFO delivery protocol? We talked about that a little bit. We have a couple of choices. So we could put sequence numbers on messages, right? Or we could require an acknowledgement before the next send, or both. So we could do something like numbering these messages and then not delivering them unless they're the next one in the sequence, or we could have this back and forth where acknowledgements are required. So that's FIFO delivery. Cool. What about causal delivery? So what does the causal delivery guarantee say? It says that if the send of message M1 happens before the send of message M2, then the deliver of M1 happens before the deliver of M2. And a violation of that guarantee would look like this. Our classic causal anomaly. What do we do to ensure causal delivery? Vector clocks. Or we use some kind of, for this, we can use some sort of causal broadcast algorithm. And the causal broadcast algorithm is based on vector clocks. So processes keep track of their own vector clock. We attach vector clocks to messages when we send them. And before we deliver a message, we check its vector clock to make sure it's not from the future. So that's what you do to enforce causal delivery, at least in a broadcast setting. How about totally ordered delivery? What was the guarantee then? If a process delivers M1, then M2, all processes delivering both deliver M1 first. And here's our classic picture of what a violation of totally ordered delivery would look like. Did we talk about a protocol that we could use to enforce totally ordered delivery? We did not. We just talked about how it was hard. So that said, here's something you could do, right? Have another process running over here. And then anytime, remember that we were talking about these being clients and these being replicas. So the idea here is that the clients are the only ones sending the messages and the replicas are receiving them. So have another process over here. Call it maybe like coord for coordinator. And anytime a client wants to send a message, it has to check in with that process first. Then that process tells the other processes the order in which to deliver the messages, so they all agree. So these clients would have to first go over here to talk to the coord process and say, hey, I want to send a message. And then the coord process would then manage the sending of that message to the replicas. And same here, this would have to check in here. And then messages would go to here and here. Okay, so that would be one way of enforcing totally ordered delivery. What's wrong with doing it that way? It's slow, right? So problems with this. It's slow. Why is it slow? Because the coordinator is a bottleneck. Is there anything else that's wrong with this? Yeah, if the coordinator crashes, right? So this approach isn't great. We'll come back to this later in the course. I only draw this picture to demonstrate that it is possible to enforce totally ordered delivery this way. It's not a great way, though. So one thing that I want to talk about in the last 5 minutes that we have here. So all these properties that we've talked about. So we talked about FIFO delivery. So FIFO delivery, causal delivery, and then totally ordered delivery. All these properties that we've been talking about, these are all specifications of how some protocol or algorithm should behave. And in particular, they're what are called safety properties. So what does that mean? So any property that we talk about can be thought of as a safety property or a liveness property. Or some combination of the two. So what do those terms mean? What is a safety property? So colloquially, a safety property tells you that something bad won't happen. So we know that a property is a safety property if we can point at something that violates it in a finite execution. So, for example, this is a finite execution that violates the FIFO delivery property. Well, these lines go on forever, so maybe it's not finite the way that I drew it, but we could make a cut right here, look at the events and messages that are in the cut, and then say that's a violation of FIFO delivery. So we know that FIFO delivery is a safety property if we can point at something that violates it in a finite execution. What about causal delivery? Is that one a safety property also? Sure. We could violate causal delivery in a finite execution. Totally ordered delivery, same deal. So the fact that all of these properties can be violated in a finite execution means that they're safety properties. A liveness property, on the other hand, says something good eventually happens. So an example of a liveness property would be something like the system eventually responds to every client request. So if you have an execution like this, say you have a client and then a system and then a request. So let's pretend that the system is just one process right now. In reality, it might be many. Here's a request. Time goes by here, right? Crickets are chirping. Does this execution violate the property that the system responds to every client request? What do you think? Yeah, no, not if eventually has no time limit, right? So the property hasn't been violated yet. So liveness properties do not have finite counterexamples. In other words, I can't draw a picture of a finite execution that violates a liveness property. I can draw lots of finite executions that satisfy the liveness property, but I can't draw a picture of a finite execution that violates it. And liveness properties are usually considered harder to reason about than safety properties. And the trouble is you really need both, right? So we're out of time. So we'll begin talking about this more next week. And then this is gonna lead us into our next topic, which is gonna start to talk about fault models and failure. See you next time.